I hope I'm pronouncing this correctly, and it is on dismountability in temporal clicks revisited.
Thank you. So I will talk about dismountability in temporal click. This is a joint work with Nocaste and Timothy Corsini. And I will start from the definition of temporal. Okay, I start from the definition of temporal graph, even though Michelle already covered every version of it. So when I speak about temporal graph in this setting, I will, let's say, in general, a temporal graph, it's a graph plus a function that assigns a set of labels to the edges. And usually we call the static graph, the underlying graph of the footprint. And in this paper, we consider proper temporal graphs. And this means that two incident edges share no label. For example, in the picture, we have multiple labels that are incident to the same vertex. So to make it proper, we remove some of them. And we say that the graph is simple. It's if each edge receives only one label. And again, this graph is not simple because of the presence of two edges with two labels. We remove some of them. We make it simple. And we say that a simple and proper graph is happy. And from this point on, I will consider only happy graphs. And a temporal graph in this setting, it's a path with increasing times. And for example, in the picture, we have a path from vertex B to vertex C going through A and D and using time 1, 2, 3. And we say that temporal graph it's temporally connected if all pairs can reach each other. And one may check that this temporal graph is temporally connected. I will drop the adjective temporal because otherwise it will be annoying. So the problem that we will cover is the one of studying minimal spanning subgraph that preserves temporal connectivity. This in the static setting, it's like asking for a minimum spanning subgraph that preserves connectivity. And we all know that the answer to this question is a spanning tree, and the existence is guaranteed, and the size is always n-1. In the temporal setting, we are given a temporal graph, and the goal is to remove edges or find a subgraph of it such that it contains a minimum number of edges and it preserves the temporal connectivity. And the existence is guaranteed because we can just pick the graph itself, and the complexity actually is open. And even though there have been rumors that this has been solved some week ago. And we will look to the question, is there any guarantee on the sides? So first result comes from gossip theory in 1979. Saying that the absolute minimum for this problem is 2n-4 in the sense that you cannot temporally connect a graph if you are given less than this number of labels. And so people wondered if, like in the static setting, we can always guarantee a spanner of linear sides. And they come, and the answer was negative. It was proved that there exists a family of graphs with a labeling that that has n log n, asymptotically n log n edges and cannot be sparsified. So they moved to the question, can we guarantee at least something a bit less than quadratic? And the answer is again no. Axialis and Fotakis proved that there exists a family of graphs that has roughly n square edges and cannot be sparsified. On the positive side, we have that optimal spanner, let's say linear spanner, exists as soon as the random temporal graph becomes temporally connected. And instead, in the deterministic setting, the research they have concentrated in proving something about cliques, and Castelliters and Schulters proved that in temporal cliques, spanner of sides and big O and log n are always guaranteed. And this was achieved using dismutability plus a bunch of other techniques. And in fact, this talk we will show that dismutability is, in some sense, all you need for this result. So, what is dismutability? Dismutability is like this principle: if you find a node, in its general version, it's like if you find a node that a node plus an incident edge, such that it can after that edge, it can still reach everyone. And another edge incident to this vertex that I am considering that can be reached by everyone, then I can remove the vertex and find a spanner in the resulting instance, and then just attaching those two edges will give me a solution for the problem. If we restrict this to considering only minimum and maximum edges, dismutability will say if you can find a node such that it receives the minimum edge of someone else and the maximum edge of someone else, then I can remove it. Why? Because we are in a temporal clique, and since, for example, the edge UB is the minimum for B, it means that after the time of this edge, it will still reach everyone else because it has a direct edge, not in the sense of directed, a direct edge to those vertices. And so if you can find a vertex like this, you can store those two edges, recurse on the residual instance, and once you found a spanner, you will attach those two edges, and all will work good. Let me go through an example. So in the picture, the top vertex receives the minimum of the bottom right and the maximum of the center left. And so we can remove it. And we can remove at each time step. We find a vertex that receives a minimum and a maximum. We remove it. We continue, and in the end, the spanner will look like this. And in fact, if this is recursively applicable, then it gives you a spanner of size 2n-3. The problem is that it's not always it is possible to find a dismountable vertex. So we relax a bit the definition of dismountability, and instead of using all the edges, we use paths. So in this definition, we'll say that a vertex U is dismountable if there exists a path from U to B ending with the minimum edge of V, and another path from a vertex W to U starting with the edge, the maximum edge of W. And we select both paths for the spanner, and we record some distance in which I removed only the vertex U. And if this is recursively applicable, then for some k constant, then we obtain a linear spanner once again. Again, this is not always applicable, but the absence of this kind of vertices give rise to an interesting structure. So let me start from the definition of two sets. So I will call D minus the set of all the vertices that receives the minimum edge of someone else. And B plus the set of the vertices that receives the maximum edge of someone else. And it's easy to observe that if a vertex belongs to both sets, then it means that it's one of dismountable, because it's just how we define the one of dismountability. And so in clique that do not contain one of dismountable vertices, we can partition the vertex set into three sets: V minus, V plus, and the remaining one, V0. Or alternatively, we can define V0 as the set of vertices that do not receive any minimum or maximum edge from any other vertex. Now we see that if we pick two vertices in B plus and look at their minimum edge, if these two edges collide in the same vertex of V minus and collide in the same vertex V minus, then one of the two will become two of dismountable. Well, because one of the two can go through both edges, so arrives to the other point using the minimum edge of that point. And by definition, in the picture, V receives the plus of theta because it belongs to V plus, so it must receive the maximum edge of someone else. And if we forbid this pattern, we have some consequence, and the first consequence is that if we look to the minimum edge of all the vertices in V plus, this forms a matching, and the same on the other side if we look to the maximum edge of the vertices in V minus. And also that these two together implies also that V minus and V plus are of equal sides. So the question now is, where are the vertices of V0? Well, they are here, but they send their minimum to some vertex in V minus, their maximum edge to some vertex in V plus, but they do not participate in the matching. Let's look to them closely. So we have our vertex W that belongs to V0. It will have a minimum edge and a plus edge that will go to, let's say, V1 and V2. And now, since V1, because of the two matching, there should also exist U1 and U2 that sends their minimum, the minimum edge of U1 it's sent to V1, and the maximum edge of U2 is sent to V2. And also, since U1 belongs to V plus, there should also exist some vertex X that send its plus edge to U1. Now let's look at the label of this pattern. So if A is less than B, then U1 is two-op dismountable because it can reach W through its minimum edge, and it receives the maximum edge of someone else. So if we are forbidding two-op dismountability, this cannot happen. So we have the other direction. And the same can be proved for C and D. And so we must have that D is less than C. But in this case, W is two-op dismountable because it can reach U1 through its minimum. It can be reached by U2 starting the path with the maximum. Conclusion, if G is not one two-op dismountable, then V0 must be empty. So to summarize the structure of non-one two-op dismountable clique, we have that V and V plus are of the same size and form a partition of V. The set of the minimum edges of the vertices in V plus forms a perfect matching, and the same for the maximum edges. And actually, it can be proved that this is an if and only if. What about then three-op dismountable clique? Well, it turns out that only forbidding two patterns in a non-one two-op dismountable clique will give you a non-three-op dismountable clique. And those two patterns are basically saying that if I pick two edges in the minus matching, let's look at the left figure. If I pick two edges in the minus matching, then the edge between the two vertex in V minus cannot be in between the time of these two edges, because otherwise I would have a three-op dismountable vertex. So if we forbid this, then the clique is not 1 to 3-op dismountable. And actually, something more is true. It's that if the clique is k-op dismountable, then the clique must be 1 to 3-op dismountable, or in other words, if the clique is non 1 to 3-op dismountable, then it's not k-op dismountable. And this is proved by contradiction. I don't know if I have the time to cover this. And so this has, so the fact that KO dismountable click implies 1, 2, 3 op dismountable. I'm sorry. The fact that KO dismountability implies 1, 2, 3 op dismountability has some consequence. The first one is that we can stop the analysis at k equal 3. And the second one is that any minimal countersample to the existence of foreign spanner must have all the properties of non-1, 2, 3 op dismountability. And as far as linear spanner are concerned, excluding just 1, 2 op dismountability, it's sufficient. Why? Because as we have seen, if we forget about the edges inside the two partitions, D minus and D plus in non-2 op dismountable click, then this graph has a special structure, which what has been called the extremely matched. That is, there are two perfect matching. One is formed by reciprocal minimum edges, and the other one is formed by reciprocal maximum edges. And this kind of graph is temporally connected, because, for example, if a vertex on the left wants to reach a vertex on the right, you can just pick the edge that the direct edge that it has with it. If a left vertex wants to reach a left vertex, then it can go on the right using its minimum edge, and then by picking all the other star, it will reach every other vertex. So, and we also have that, obviously, if you can find a spanner in this subgraph, then it will also be a spanner for the entire click. And something more general, it's true about this class of temporal graph. It's that extremely matched big click, so the graph on the right with the two extremal match, admit linear spanner if and only if the click admit temporal clicks admit linear spanner. And we'll cover this is not a result of this paper, but it's a result from Henrik et al. And they worked in extremely matched temporal big click, and they focused on preserving the reachability from left to right only, because along with the two matchings, this gives you that the spanner is temporally connected. And they proved, well, Peter Schulte proved that big O and log n spanner always exist, and Henrik et al. Gave a much simpler proof for it. And the proof is because basically that we split the work of the left. So we want that the left reach the right. So we split the left in two, and we keep, and we want to find for each of them a spanner that all left reaches or right, okay? And so to summarize it, we can split the work. Then we can dismount the vertex on the right that collide on the left, which the maximum edge collide on the left. And we can recurse on this. And if someone does the math, then we will end up with a spanner of big O n log n. And on the other side, another technique to find spanner in temporal graph, it's the one of pivotability. This is just an edge such that, a temporal edge such that can be reached by everyone before its time, and after its time can reach everyone. And if you find this in a temporal graph, then you got a 2 and minus 3 spanner, you are very happy. But this not always exists in temporal graph. And we also proved that actually the class of recursively dismountable clicks, it's a subclass of the pivotable one. Yeah, thank you.
Thank you, Daniele. Any questions?
Can I ask what was the question you teased? You teased the question at some point that might have been solved. What was it? At some point in
the complexity of this problem but not on temporal clicks. In general, on temporal graph, on temporal LP graph, whether it's NP complete to find the minimum temporal spanner.
Okay.
Yeah, sure.
I can keep going with questions.
Sure.
So, I mean, question to you, which you might know, like, has Arnaud answered the question about linear spanners yet, or?
No.
So that question has not been answered, because I think your work kind of builds up on it, and I was wondering whether you had guys that actually got to a solution to that, whether linear spanners exist or not.
No.
No. Okay.
We would be very happy, even if someone else found it, because.
Thank you.
Yeah, thank you.